Myself, Nagarajan, Assistant Professor in EC Department, Rohini College of Engineering and Technology. In this course, let me see about the embedded system and IOMT for biomedical engineering. So let us see the hardware and von Neumann architecture. First, we want to define what is computer architecture. So computer architecture is defined how a computer system organizes its component to process information. So two primary architecture in embedded systems are there. One is a Harvard and von Neumann architecture, each with different memory and data processing design. So let us see the first architecture. It is a von Neumann architecture. So in von Neumann architecture, it has a single memory system. In the von Neumann architecture, a single memory space is shared by both instruction and data. The processor fetch instruction and data from the same memory one at a time using a single bus system. Sequential execution. Instructions and data cannot be accessed simultaneously because they share the same bus. This leads to phenomenon known as a von Neumann bottleneck, where the CPU is ideal while waiting for memory operation. It will be do one at a time, one operation only. So despite this limitation, the architecture is simpler and more cost effective, making it popular in general purpose computing system. Flexibility. So the shared memory model allows dynamic allocations where the same memory location can be used for both code and data, providing flexibility in memory usage. The architecture is widely used in system where resources optimization and cost are critical factors. Examples of a von Neumann architecture is a CPU. The traditional PC architecture is an example of von Neumann architecture where the CPU fetches both instruction and data from the same memory. Now let us see the Harvard architecture. So in Harvard architecture, it has a separate memory system. The hardware architecture features separate memory spaces for instruction and data, each with its own dedicated bus. This allows simultaneous access to instruction and data, which can significantly speed up processing by reducing the waiting time for memory access. And also, Harvard architecture has a parallel execution. With the separate buses, the processor can fetch an instruction while reading or writing data, enabling parallel processing of data and instruction. This parallelism is particularly beneficial in real-time embedded system where timing and speed are crucial. And next one is a increased complexity. While the hardware architecture offers performance advantages, it is more complex and expensive to implement than the von Neumann architecture. So, the complexity arises from the need to manage two separate memory spaces and buses. Now, let us see the examples of a hardware architecture. Modern digital signal processor and microcontroller often use a hardware architecture, especially in applications like audio processing, telecommunications, and high-speed data acquisition. So let us see the comparative analysis of a hardware and von Neumann architecture. First, let us see the performance. In this performance, that is a hardware architecture typically outperforms von Neumann in terms of processing speed due to its ability to execute instruction and access data simultaneously. And next one is a memory efficiency. When we think about the memory, the von Neumann architecture is more memory efficient when compared with the hardware architecture. So In a hardware architecture may require more memory as code and also a data are stored separately than uses cases. In one Neumann architecture is preferred in application where cost and simplicity are more important. But in hardware architecture, it is chosen for high performance embedded system. And next, let us see the CISC and RISC architectures. So, first of all, let me see about the instruction set architecture. So the instruction set architecture defines the set of instructions that a processor can execute along with the hardware implementation of these instructions. There are two primary type of instruction set architectures are there. One is a complex instruction set computing, that is a CISC, and another one is a reduced instruction set computing, that is a RISC. Let us see the CISC architecture. It is a complex instruction set. CISC processor are designed to execute a large number of complex instructions, some of which may perform multiple low-level operations. The idea behind CISC is to reduce the number of instructions per program. And variable length instruction. It is also CISC architecture is a variable length instruction. CISC instruction can vary in length, meaning different instruction may take different amounts of time to execute and require varying amounts of memory. And next, microcode implementation. CISC processor often use microcode to implement complex instruction. The microcode is a layer of low-level instruction or firmware that translate high-level machine instruction into a sequence of simpler operation. Let us see the example of a CISC processor. In a CISC processor, Intel 86 architecture is widely used in desktop and our server processor. An IBM system, that is a 360. It is a early example of a CISC architecture designed to support a broad range of application with a complex set of instruction. Next, let us see the CISC processor advantage. It is a ease of compilation. CISC architecture allows for more direct translation from high-level language to machine code. Next one advantage is a memory efficiency. So by using complex instructions that do more per instruction, CISC can achieve the same task with fewer instructions. So let us see the disadvantages of a CISC architecture. First one is a performance bottlenecks. The complexity of instruction can lead to longer execution times, especially for those instructions that are rarely used. Next one is a power consumption. CISC processors tend to consume more power due to the additional circuitry needed to handle complex instruction and the microcode layer. Next, let us see the RISC architecture. Reduced instruction set. RISC processors are designed around a smaller, highly optimized set of instructions. It has a fixed length instruction, so RISC instructions are typically of a fixed length, which simplify the fetches and decode stages of the CPU pipeline. And also RISC architecture having a load store architecture, because it is where memory access is restricted to specific load and store instruction. This means data must be loaded into a register before it can be manipulated, and a result must be stored back into memory afterward. Now let us see the examples of a RISC processor. It is a ARM architecture. Most of the mobile devices and embedded systems are using a ARM architecture, then MIPS architecture. Now let us see the advantages of a RISC architecture. It has a performance wise, that is a RISC processor can execute instruction more quickly when compared with the CISC. Next, power efficiency. With fewer transistors dedicated to executing complex instruction. Let us see the disadvantages of a RISC architecture. It has a increased instruction count, and also it is a complex compiler design. So in this video we discuss about the what is instruction set architecture, and also we discussed hardware and von Neumann architecture. We discussed CISC and RISC architecture. I hope that all of you understood about this topic. Thank you.